Hello, I am Simply Positive, and today we will cover the first lesson of category theory. In our last video, we introduced this course. I broke down how the series would be run, and I also defined the terms definition. Sorry, I don't know why that's selected. Try that again. I broke down definition, mapping, and the tag system. That was the previous video. And I told how a definition is the term followed by a colon, followed by either a description or a mapping. A mapping is an arrow from thing 1 to thing 2. And the tag system is going to be our way of telling what from what, of telling what from what. So it's going to be the tag followed by the name of the thing that we are describing. And those are pretty much the prerequisites to category theory. In today's lesson, we will cover 4 core topics. Okay? So we will cover what is category theory, we will cover what makes up category theory, we will cover what is a category, what makes up a category, and finally, how do we define our category? Okay? So here are the terms for today's lesson. I'm going to type them out, but please feel free to pause if you want to write them down on your own. So we have category theory, we have what a category is, what an object is, element, the sub prefix. We have morphisms or morphism / function. We have functor, natural transformations, commutative diagram, and finally, a proposed category design process. Okay? So here are our terms. Please feel free to pause the video to write them down. And now, without further delay, let us begin. So, what is category theory? Category theory is a framework for defining and describing how things relate to each other. What are the 4 things of category theory? Well, we have categories, we have objects, we have elements, and finally we have various mappings. So, what is a category? A category is a collection of objects and their mappings. Okay? So when you think of a category, think of it as your own made-up universe. So I'm going to put this in parentheses, a universe. Okay? It is the study of how the objects within your universe relate to each other. So then that brings up the next question. What is an object? An object is a placeholder for acceptable values. Alternatively, you can think of an object as a set of things that can be represented by that placeholder. There are some specific types of objects, but so for example, there are sets, there are groups, there are topos, there are shapes, but in reality, an object can be whatever you define it as. So, for example, you could have packs if you want. You could have troops if you want. You can have collections if you want to call it a collection. You can. It's really up to you. It doesn't matter. Just know that an object is a placeholder for what a element or what an entity can be. With that in mind, an element is the specific value or specific structure or specific outcome, even if you want, of an object. Again, an object is whatever you want it to be. So now that we have a category, an object, and an element, the way that these things relate are pretty simple. So categories house objects, and objects house elements. Okay? So then the next question is, what is a mapping? And we kind of defined it before that a mapping relates one thing to another. And there are three main types of mappings. Okay? So there are morphisms or functions that relate specifically objects to objects. There are functors that specifically relate categories to categories. And then finally, there are natural transformations, which relate functors to functors. Okay? And when it comes to categories, objects, elements, and maybe even mappings, they can all be nested inside each other. Think of it like Russian dolls, right? Those little Russian dolls that you see in antique shops or something like that. When you add the prefix sub in front of one of these four things, you can map it, you can put it inside of another thing. So, for example, a category can house a subcategory. An object can house a sub-object. An element can house a sub-element if you put your imagination to it. And if you're really imaginative, a mapping, maybe it could house a sub-mapping. Okay? Obviously, it's a lot more easier to focus on these right here that there are obviously subcategories and sub-objects, but the whole point is that things can be embedded within each other, and the way we do this is with sub. Okay? And something I forgot to mention, not only do we have the sub prefix, we also have the co prefix. And I'm going to touch on that right now. So, for mappings, in particular, if you put a co in front of it, it means the reversal of a mapping. So remember, we said before that a mapping is an arrow pointing from thing 1 to thing 2, right? Well, technically, a co-mapping is the exact opposite. It's an arrow pointing back from thing 2 to thing 1. Okay? So now we understand what categories, objects, elements, and what mappings are, as well as the 3 specific types of mappings. So all of this is used to create something called a commutative diagram. Okay? And a commutative diagram is we represent our category and how all the things are mapped to each other. So a commutative diagram is a diagram of our category and how all the things in our category map to each other. Okay, so think about it like a big web. So for example, you could call this a commutated diagram, right? Uh, A leads to B, leads to C, leads to D, right? So before we sort of delve into making our own commutative diagrams, I wanted to put forward a sort of design process to give people an easier time of making our commutative diagram. So here's a design process. When it comes to the design process, we have 3 distinct phases. We have phase 1, which is our definition and mapping phase. And it's just like how you think it is. In phase 1, we just go about setting our premises. We go about making our definitions, making our mappings, and sort of constructing our diagram that way. In phase 2, we then go to what I like to call standardization, which is whatever special mappings that we do, we rename them to whatever special subtypes they're supposed to represent. So as we go through this course, there's going to be special types of functions and morphisms, special types of categories, special types of objects. There's going to be special types of these things. And it would be a lot better to sort of condense them into what they specifically represent. And the last phase, which we're not going to cover in the sort of this particular series of category theory, I propose phase 3, which is proof. So in category theory, sometimes when you're relating one object to another, or when you're morphing one object to another, you might have gain or loss of information. So in category theory, there are specific tools that we can use to analyze how we have created our diagram. It doesn't necessarily change the diagram, it just kind of defines what we've written so far. And so that was pretty much it. And before we end this chapter, I would like to formally define a mapping. You don't have to write this down, but technically this is the formal definition of a mapping. You do not memorize this or write it down. This is just to, if for those that want a more formal understanding of a mapping or a formal structure of a mapping, this is for you. So in a mapping, remember, informally, it's going to be thing one, arrow, thing two, right? Formally, however, wherever the arrow is coming from is called the domain. So that is where the arrow is originating from. And wherever the arrow is going to, that is called the codomain. Again, remember how that co is starting to sneak in. And that is the formal definition of a mapping. Again, you don't have to memorize that. It's just something I thought I would tell you about. Oh, and finally, the arrow that is leading from the domain to the codomain is called a commutation. Okay? So that pretty much wraps up category theory. So here's our summary for today. We talked about what category theory is. It is a framework. We talked about the four things of category theory. Those things being a category, which is like a universe, and it houses objects. We have objects, which are like placeholders, which house elements. We have elements, which are the specific values. And then we have mappings, which relate things to each other. And of our mappings, we have three different types of mappings. We have morphisms, or you can call them functions. We have functors, and we have natural transformations. So functions map objects, functors map categories to each other, and natural transformations map functors. And then finally, we talked about what a commutative diagram is, which is a diagram of all of your objects, things and mappings within a category. And we talked about the design process, which includes the definition and mapping. It includes the standardization, and it includes the proof, which we won't cover until a later, a much later part of category theory. Okay? Okay. So that will conclude lesson 1 of category theory. At this time, we have technically completed base category theory. So, with our completion of base category theory, what should you be able to do? Well, you should be able to now go out and make your own diagrams how you see fit, right? You can go out, now that you know how to map things, how to define things, you can go out and technically make your own frameworks and make your own understandings of how things relate to each other, right? They may not be accurate, they may not make logical sense, but you can do that. In the next few lessons, we're going to go over what I like to call standardized category theory. In standardized category theory, we go over what some rules of category theory are, and also some special subtypes of the things of category theory, with the goal being to make more logical uh, relations in our diagrams. So to sort of make our diagrams make sense rather than just drawing arrows willy-nilly. Okay? So thank you for listening in to lesson 1 of category theory. I am Simply Positive, and I hope you see me again in lesson 2, our next video. Take care.